Good morning, class. I have posted another problem to your Canvas account. So we have a practice problem titled Momentum, the Lexus LFA. So what I want to do with you today is read the problem to you. I'm going to underline some important information. This problem does have 6 parts to it, so we're going to have to complete a graph. They do provide a T-chart, so we are provided with ordered pairs, but we do need to do some graphing, and then number 2 through 6, I will walk through all of the calculations with you. So let's go ahead and get started. The 2012 Lexus LFA has high-performance brake calipers, ceramic brake pads, and cross-drilled vented discs. The braking distance for the LFA with an initial velocity of 31.38 meters per second to 0 meters per second occurs in 48 meters. So let's go ahead and write down some important information. So our initial velocity, 31.38 meters per second. Our final velocity is 0 meters per second because the LFA comes to a stop. And our displacement during braking is 48 meters. Okay, so on number 1, they provide a T-chart for you, and it's asking for you to plot the ordered pairs on the graph. Now, in the T-chart, remember that the left-hand column represents your X value. This is our independent variable. Our dependent variable, or our Y value, is in the right-hand column. Okay, and we know that momentum depends on velocity. So when a vehicle is not moving, its velocity is 0, its momentum is also 0. And they provide this ordered pair for us. So at 0 velocity, we have 0 momentum. Our next ordered pair, at a velocity of 10 meters per second, we have a momentum of 16,140 kilogram meters per second. So 16,000. And what I'd like you to do right now on your paper is, let's just go ahead and plot these values together, okay? So 20 is 32,000. And on my y-axis, I have momentum with units of kilogram meters per second. And just for me to save room, I've said times 1,000. On your assignment, it doesn't have times 1,000. I was actually able to insert the graph with 10,000, 20,000, 30,000, and so forth. But let's go ahead and complete our graph here. Okay, and we have something that looks like that. So there is a linear relationship between the momentum and the velocity of the Lexus LFA. So on number 2, it wants us to calculate the acceleration during the braking. So what we're going to do here is use the base equation. Final velocity squared is equal to initial velocity squared plus 2 multiplied by our constant acceleration multiplied by our final distance during braking. Okay, so what we're going to do is isolate our acceleration. Okay, so the first thing that we're going to do is subtract initial velocity from both sides of the equal sign. So what I have is final velocity squared minus initial velocity squared is equal to 2 times our acceleration times our braking distance. The next step to isolate our acceleration is we are going to divide by 2 and displacement of braking on both sides of the equal sign. So on the right side of the equal sign, that cancels out. Okay? So our acceleration is going to equal final velocity squared minus initial velocity squared divided by 2 times our braking distance. So what I have is this, okay? Now, we have our final velocity. In the problem, it told us that we're coming to a stop, so our final velocity is 0 meters per second. So this guy goes to 0. So in my numerator, now we cannot get rid of our minus sign here. So minus, and I'm going to utilize some parentheses here. My initial velocity is 31.38 meters per second. We're going to square this value. Now we are not squaring this negative, okay? We cannot distribute the negative in here because we have to take care of our exponent first. We're going to divide this by 2 times our braking distance, which is 48 meters. So in our numerator, let's go ahead and take out our calculators. So 31.38 meters per second squared gives me 984.704. And remember, not only are we squaring the numerical value, we're also required to square the unit value, okay? And we also have to apply a negative to this value. So in my numerator, I have a negative 984.704. We're squaring meters per second, so that's going to give me meters squared per second squared. And in our denominator, we have 2 times 48 meters, 96 meters. Okay, so before we complete this, what I want to talk about is this negative. Okay, so what we have is our sports car. We're traveling in a positive x direction. Our initial velocity is 31.38 meters per second. And then we slam on the brakes and we come to a stop. So our final velocity is 0 meters per second. So when our final velocity is less than our initial velocity, that means we're going to have a negative acceleration. So our initial velocity is in the positive x direction, but since our final velocity is less, that means we're going to have a negative acceleration. So our acceleration vector will point in the negative x direction, okay? So I'm just going to go ahead and draw that right here. So our acceleration vector is in the negative x direction. So let's go ahead and divide this here. And this is going to give me a negative 10.257. Now let's take a look at our units. So in the numerator, we have meters squared per second squared. In our denominator, we have meters, which is meters over 1. When we divide fractions, it's like multiplying by the inverse of the denominator. So meters squared per second squared times 1 over meter. So one of our meters is going to cancel, giving us meters per second squared. So for number 2, negative 10.257 meters per second squared, okay? So we are slowing down. We have a negative acceleration. Okay, number 3, the time to stop. So what we can do is use the equation. Our acceleration is going to equal the object's change in velocity divided by the time interval. Now, what I want to do to solve for delta t is to multiply delta t on both sides of the equal sign, and then we're going to divide by our acceleration, which will give us delta t equals delta v divided by our acceleration. What I want to do is expand this numerator here. This is final velocity minus initial velocity. So remember, our Greek letter delta here represents change in. So the change in velocity, final velocity minus initial velocity. Now you know the problem already tells us that the final velocity is 0 meters per second. Okay, so I have a negative initial velocity divided by our acceleration. So in the numerator, I have a negative initial velocity is 31.38 meters per second. In my denominator, my acceleration, now we have to use our calculated value from the previous problem. So negative 10.257 meters per second squared. And we can never have a negative time value. So right here, this is going to work out perfectly because the negatives are going to cancel. So we're going to come up with a positive value. So 31.38 divided by our negative 10.257 is going to equal delta t is 3.0593. Now let's take a look at the units. So I have meters per second divided by meters per second squared, and we're going to multiply by the inverse. So seconds squared over meter. Our units of meters will cancel. One of our seconds cancels, leaving us with units of seconds. So we know we're on the right track here because the base unit in the metric system for time is seconds. So we're good to go. 3.0593 seconds. Okay, let's move on to number 4. Now in number 4, it's asking for us to calculate the mass of the Lexus LFA. Now, what we have here is ordered pairs for our graph here, velocity and momentum. We know that the momentum of an object is the product of the object's mass and the object's velocity. So we can use any ordered pair here to solve. So we're going to solve for the mass. So mass, I'm going to divide by the velocity of the LFA on both sides of the equal sign, which will give me momentum divided by velocity. And we can select any ordered pair here, and I'll just select this ordered pair. So my momentum at 10 meters per second is 16,140 kilogram meters per second. I'm going to divide this by the velocity, which is 10 meters per second. 16,140 divided by 10 is going to be 1,614. Now let's take a look at our units here. Kilogram meters per second. And we're dividing fractions, so let's go ahead and multiply by the inverse of the denominator, which is seconds over meter. Our units of meters will cancel, and our units of seconds will cancel, leaving units of kilograms. And so we know units for mass in the metric system is kilograms, so we're on the right track here. 1,614 kilograms. Okay, moving on. Let's take a look at number 5 together. Number 5 wants us to calculate the braking force using the impulse momentum theorem. So what I've done here is I have written a subscript of IMT representing impulse momentum theorem. And that says the impulse applied to an object is going to be equal to the change in momentum for the object. So what we have here is our braking force multiplied by the time interval of braking is equal to the mass of the LFA times the final velocity of the LFA minus the mass of the LFA times the initial velocity of the LFA. Now, you know that the final velocity of the car is 0 meters per second. Remember, they gave that to us because the car comes to a stop right here. So this is going to be 0. So what we have here is the force of braking multiplied by the time interval of braking is going to equal a negative mass of the car times the initial velocity of the car. Now, the question is asking for us to calculate the force of braking. So we need to isolate this variable. We're going to do that by dividing by the time interval on both sides of the equal sign. So what I have is the force of braking is equal to negative mass times initial velocity divided by the time of braking. Okay, so this is going to equal a negative. Now for mass, we're going to have to use the calculated value from the previous problem. So 1,614 kilograms. Our initial velocity, 31.38 meters per second, and we're dividing by the time of braking, which is, we're going to use our calculated value, 3.0593 seconds. Okay, so let's go ahead and resolve the numerator first. And that's going to give me a negative 50,647.32 kilogram meters per second. And we're going to divide this by 3.0593 seconds. And this gives me 16,555. Okay? Now we have a negative here. And the value is negative, but I want to talk about this negative value before I write that down and talk about units. So, in the diagram that we drew earlier, our acceleration vector is pointing in the negative x direction because we're slowing down. Our final velocity is less than our initial velocity. And according to Newton's second law of motion, so, second law of motion is the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. So, our net force vector, this is the force of braking, will also be pointing in a negative x direction. So, our net force applied to our car is in the negative x direction, therefore our acceleration is also negative. So we have a negative 16,555. Now let's take a look at the units. In the numerator here, I have kilogram meter per second, and we're dividing this by seconds. And algebraically, that's seconds over 1. So what we're going to do is multiply by the inverse of the denominator. So kilogram meter per second times 1 over seconds. This is going to give me kilogram meter per second squared. And we know that is equal to 1 Newton. So the answer for number 5, negative 16,555 newtons. Now let's take a look at number 6 and we can finish the problem here. Number 6, the force of braking using Newton's second law. So I provided a subscript here, NSL, which represents Newton's second law. And we've actually already talked about it a little bit. This is our equation right here. Now, what we're going to do is solve for the net force applied to the object by multiplying mass on both sides of the equal sign. So F net is equal to the mass of the LFA multiplied by the LFA's acceleration. So what I have is our mass. Once again, we're going to use our calculated value, 1,614 kilograms. We're going to use our calculated value for acceleration, which is negative 10.257 meters per second squared. Okay. Let's take the product of these values. And I get negative 16,554.8. And we have kilogram meter per second squared, which is equal to a Newton. So once again, we've calculated our net force, which is our braking force, supplied by the brakes to be negative, so our vector's pointing in a negative x direction. So our acceleration vector is also negative. So we do have a slight discrepancy. On number 5, we're at negative 16,555 newtons. On number 6, it's negative 16,554.28. I'm sorry, 0.8 newtons. So we're only 0.2 newtons off. So there's some rounding somewhere. So doing a reality check, we're good to go here, because you know that there are 4.448 newtons in every 1 pound force. So we are just a fraction off of a pound force. So for number 6, negative 16,554.8 newtons. So very, very close here. Okay. All right, so on number 1, there are some additional ordered pairs that you're going to need to graph. I just did the 5 ordered pairs to save space on the board here. Go ahead and complete that. If you have any questions about this problem, please send me an email and I will help you. But besides that, I think we're good here, and I hope everyone has a wonderful day. Talk to you later.